and you have to do this exercise yourself to draw the trap. And you can see here 1, 2, 3, 4, 5. So only 5 vertices, very easy. Okay, I don't solve, just a kind of practice. Now we move to the second hour. Today you have to finish. We have to finish at least up to number 5 here in 1 hour or 45 minutes. We have only one general definition for the undirected draft, and now we want to explore that for specific cases. Okay, but before doing that, let me define this one first. You are given undirected draft with the vertex node vertex node V and the H set E. We define a path from some node U to other node V. Yes, is a sequence of connected nodes. So the concept connected node means if you have the first node V0, the second one V1 on the path, on the sequence of the path P, then V0, V1 must make an H. Okay, so connected, that means they make things like this one, V0 to V1, and then V1 to V2, like that one, and then V2 to V3, like that one. Okay, connected together. Then if we employ this one, then sometimes we allow some connection repeat more than once. So we restrict to the symbol path. Yes, the case where the path consists, no duplicated, that means single edges. So this one is good. Example, V0, V1, V2, V3, and you see the H here appear, once. So this is symbol path. And also we define the elementary path to be the one that consists no duplicated node. So the name different, you see. Symbol path means no duplicated edges. Elementary path means no duplicated vertices. Okay, and in Vietnamese language, they also employ different name for that one. The first one we say đường đi đơn, you see, symbol path. The second one we say đường đi sơ cấp, okay, elementary path. So let's see how can we move with that. Complete draft mean like this. Okay, if I give you the number of vertices to be number 4 on the right hand side here, number 4, then a complete draft defined on 4 vertices. We denote by key 4 like this. Will be just a simple draft that contain exactly only one connection between each pair of distinct vertices. So very important, right? So if I denote the first one here A, and I denote this one to be B, the third to be C, and the last one to be D. Okay, so this is the beginning A. Then you see between A and B you have only one. Okay, only one edges, and that's true for AD and AC as well. So if you count, you see that there are 3 connections from A. We can say the degree of A to be number 3. You see, 1, 2, 3 edges, and the same must be true for the other one as well. The same thing happening for B, because if you choose B, then there are only 3 other vertices, A, C, D. And from B, you can connect one exactly to A, to C, and to D. And that's also true. And if happening for any vertice in K4, then we get a complete draft. Okay? So you observe this one. Degree of A, of B, of C, of D, all become number 3 in the right hand side draft, you see. And number 3 here actually equal to the total number of nodes minus 1, you see. And that observation also true for the second graph on the left. We have complete graph on 5 vertices. And you should try yourself to understand the left figure. Now we move to the cycle. The cycle are different from the complete. The cycle you imagine is the kind of, discrete version of the circle. Circle in your high school. In high school, you draw a circle like this one, and that considered to be infinite vertices. Now we restrict to the right hand side, for instance. Again, I choose n to be number 4, and we get a cycle if the picture of the graph like this one. The number of edges is smaller than the complete K4, because now we allow only the surrounding connection. So you go from A to B, and then from B to C, and go back to D, and from D you get back to A, and that means the total number of connection exactly also to be number 4. So if we did not aim to be the number of connection or the number of edges, then we can say the cycle, we did not by C n like this one, consists n vertices, of course, and also right here n edges as well. So the surrounding V1 to V2, yes, V2 to V3, B to C, yeah, etc. And finally V3 go back to V4. So 1, 2, 3, 4, and this one, the last one here, go back, you see? And the same thing happening for C5. The number of vertices equal to the number of edges. So for the left hand side, you have m to be number 5 as well. Okay. So after you define, then you see that in a cycle graph we can find a symbol and a closed path. So the path we start from A like this one. I denote the path by P. Okay. I go like this one, and I go to this one, and I go to this one, I go back to here. This one we call an open path. But if at the point here I not stop, but I continue go back to the original one right here, that means we make a cycle. Okay, so we call that a closed path, exactly, and connection. So this is the property we know in the cycle graph. But the problem is we ask the other way question. Any graph, even if have, at least n connection, can we make that a cycle? So this is a different way, okay? In a cycle, you can find a closed path. That's correct. We just done that by drawing the picture here or the picture there. But the other way around, I'm not sure. So that's why we put the question here. Any graph, can we make a cycle? Even the number of connection, at least n. The answer in general case will be no, not one way. Okay, you have to be careful with the other way around of the story. In mathematics, the inverse, the reverse argument not always true. Okay, when you learn logic theory, you remember in chapter 1 with Dr. Tungan, you remember in logic theory you have decision. You have A imply B, but in principle you don't have B imply A. So be careful with that kind of argument. So I recall that one in the chat box. You can read now. Okay. A imply B. Then in general, not equivalent to say, not equivalent to say that we also got B implied. So Lê Hoàng say no. Good answer, yes. So that's why we see that, okay? Now the third concept here, wheels, in Vietnamese is like this one. A wheel is just kind of circle and you get to be cycle, okay? You have a cycle and you put another vertex we call the center inside, and then you connect that new center to the one on the cycle outside, and the full picture will make you a wheel. So that's all. So we can say the wheel will be the union of a cycle with a center. That's all. Okay, I am drawing the way we make the W form. See? And then the small exercise will be write the adjacency matrix of this one. Something happening. Something happening there. What happened there? Sorry, the connection was lost. Now, do you hear me again? Recovering from lost connection. Do you hear me? Yes or no? You hear me and you see the slide? Okay, here again, please. Got back. And also the slide. Yes, okay. Now, please pay attention. The next structure is not simple. Okay, pay attention. The third, the fourth special trap, we call the hypercube with 2 power n nodes. So this is definition for that. So we say an n-dimensional hypercube denoted like this one is just a graph that have vertices representing the 2 power n the bit string of length n. Okay. Then we say the vertices connect together or they are adjacent if the bit string they represent differ exactly in one position. So this is the longest concept so far. Pay attention to this one. Okay. So that means if I get n to be number 1 and we talk about the bit string, that means you have only 2 strings, 0 and 1. Understand? Okay. But if I get n to be number 2, then we talk about the different bit strings. How many strings are there, people? If n to be number 2. Four. So right here, look to the picture. They are 0, 0, 0, 1, 1, 0, and 1, 1. So work on cell number 4. So that means we have 4 nodes. Then we put the node inside the set of nodes. Remember, by our original definition. Okay. So look to the chat box. I write the full list of nodes. So we finish the first part here. The vertices present in total 2 power 4, which is like this, right? Then what are the connections? The vertices adjacent if the bit string exactly differ in one position. So tell me, if we choose the first one string and the last string 0, 0 and 1, 1, then tell me how many bits different between the two. 2. Look, Watson said 2, right? Good. So what the difference between this one? 1. Fine. So you see in the second picture in the screen, I draw the hypercube for the case n to be number 2. So we allow connection like this one. Only 1 bit different. We allow this one. We allow this one as well. But we do not allow this one. Because your friend answered that there are 2 bits different. Not allow an edge. Okay? No connection between 0, 0 and 1, 1. Now we move to the next picture. I give you n to be number 3. Then the hypercube defined on n like this one give you in total how many nodes are there? Right? 8 nodes. And you can draw them in the picture. The problem the same. You want to connect 0, 0, 0 with some connection to some node, then you have to make sure that there is exactly 1 bit different like this one. So this one is okay. How about this and this one? How many bit different between? the two not like this one. You observe and you get number 2. So therefore, that's easy, okay? Now we consider any n. Then you can write any knot by using abstract notation. I denote by U1, U2, U3, up to UN. Understand me? Then after that, you get the second knot V. V1, V2, V3 up to Vn. So this is the zero case. Okay? Then how do we know that they are different in exactly one position? Then you have to define the concept we call the Hamming distance. Copy the chat box information, please. We define the Hamming distance between two knots U and V by this notation. Summation index I, where you get UI minus VI. Okay? Then tell me what is the range of the distance between not U and V. What is the possible value of the Hamming distance U and V? What is the possible value of the UV? Lê Hoàng say the first question incorrect. Trần Ngọc Quan, yes, 1 is correct. The value of D going from 0 to n. Okay, so apply this one. I can compute, for instance, look to the picture. The distance U from U to V, like this one. And you see that this and that equal, then the gap between position will be 0. And this and that, again the same 0. That means the last bit provide the gap will be number 1. And if you take the sum, you get the number 1. Okay? And you say that the knot U here and the knot V here, they have the Hamming distance to be number 1 exactly. Therefore, you can draw an H like this one. You see? But because one answer this, so I would like to ask one about this. Look to the chat box. Tell me the outcome of this one. 1. Trần Ngọc 1, answer me. What is the value of that distance? 3, wrong. The other guy, the second one, wrong. Huh? Number 3, let me check. Okay, let me check. One say number 3. The second one, Nguyễn Viết Hòa. Nam Khánh, wrong, but 1 and Hòa I see again. They say number 3. And we check on the trap, the gap between here and there, 1 unit. And 0 here, 0 here, and gap with 1, 1, 2. Therefore, the answer of the distance will be like this. Correct? Bravo. Okay. So 1, Today she got this, and Hòa hả? Nguyễn Viết Hòa, right? Nguyễn Viết Hòa get number 1. Okay. So I will keep track this one later on my profile about your contribution today. Nguyễn Viết Hòa, yes, 1. Okay. So that's fine. So be careful if the value m bigger, then you cannot draw the graph. Right now we draw Q1, Q2, and Q3. So I ask you to do this exercise at home yourself. How can we draw the hypercube with n? To be number 4, the last question here, Q4. And you have to draw the graph, and you have to make the adjacency matrix of Q4 as well. Q4, Q3. Okay. Yeah, do this at home, not now. Okay. Do this at home, not now. You have to draw at home. We have to move on here. We discussed this before when we talk about the undirected graph, so I just remind this one very quickly. You have two vertices U and V, so the connection from U to V, like this one for the undirected. This is the endpoint, this is also the endpoint. But if you have the directed, you have to put an arrow like this one, and in this case, the not U, we have to call initial of the connection. Okay, and the second one we call the terminal. Okay, V to be the terminal. If you have things like this one, you have some loop in the directed graph, then must be saying that initial and terminal of a loop are the same. That is trivial, right? Then we can define the degree in the directed graph as well, because in the directed, the direction is important. So if I choose this one to be the node, and the direction like this one, you see, or I choose U and V are different, then you have something like this one. Look to the picture I am drawing. Then you have V connected to another node denoted by W, and you see like this one. You see? Then you have to tell about U and V going. We call the in degree. This is notation, and the in degree of V will be number 1. But also you have the connection from V to W. We talk about the out degree, okay, denoted by this one. In the picture also number 1, okay. So 1 degree in and 1 degree out for the node V. So that is the extension from the undirected graph, okay. So for the directed graph, you have to say in degree and out degree. So therefore, the Hansakin theorem before, when you extend to the directed graph like this one, you have to be careful. The right hand side here is just the number of directed edges. You don't have the reverse theorem. Now you say that M equal to the sum of out degree. When you take the sum on the node set, okay, that also equal to the sum of in degree. So pay attention to the minus and the plus here. So this is extension from the Hansakin theorem, okay. So we move on with the application of the specific graph so far up to the hypercube. And this is the second group of exercise today. You have to do weekly at home when you learn the theory. Exercise number 5. Figure out the function. Exercise number 6. Underrated. This one also underrated. Okay. You have to prove, formulate this one happening in any symbol trap by your mathematical argument. Okay, in line the theory. Then section B and C here as well. There are sometimes the proof is not easy. You have to write down the full argument. In particular, the last one here is not easy. You have to write that argument carefully. Okay, at least two vertices of the same degree in any undirected symbol trap. So exercise number 6 is very meaningful to consider. 7 exercise. You may do exercise together in the home. Also, sorry, in the problem solving session together in the HCMUT. So this is on. So practical problem. So there are the argument, the question you have to prove. Okay, you have to model the problem by a graph. You have to model this problem by a graph. Okay, and this assumption tell you that the graph must be undirected. Okay, because you say if A no B, then we conclude B no A. So we don't have the direction here. We have undirected graph for this case. So there are a few exercises you have to practice at home, a few hours at least, before we move on with the new theory. This is the review exercise. Have to write arguments fully for that. Okay. About just to name it. So there are a lot of things you have to prove. Okay. This is our assumption, and this is the first question, and this is the second question for this exercise. The best strategy should be trying with minimum number n. You should try n with value 4. The minimum value of n to be number 4. Okay, and figure out the method and then write the solution in the general case. Okay, so for the revision exercise, I suggest that you should start with the minimum value and number 4 to figure out the method. Then you can increase n from number 4. Then you may think about number 5, and then in the last one here I ask you to prove for 6 people. Okay, so extension step by step to prove. So for computing student, without solving the exercise, you cannot understand the theory. A lot of exercise for you. Okay, computer science student need to be smart and do it yourself. Here, now we extend n to be number 7. You see, smaller and then bigger and larger, and the problem also are different. Now finish the exercise. I have to continue the theory. We move to the 6th specific trap. This is considered is one of the most useful structure and draft in reality, but the bi-baptide. We read this one pi baptide draft. So this is the informal definition. Briefly mean informally, okay? A simple graph we call bipartite if the vertex can be split into two disjoint set A and B. Disjoint mean like this one, right? Split partition into, that means you have this equality, and then so that every connection in the graph must connect a vertex in A and a vertex in B. That's fine, from A to B, but not connection between two vertices in the same A or two vertices in the same B. So the first one we call decomposition of vertex. Okay, this one can be rewrite here formally by this notation. But the second condition about the H or the connection here, you have to be careful, because we say that actually formally to say the N naught must belong to different subset. You see, we do not allow U and V at the same time belong to A or at the same time belong to B. You see what I mean, right? So that means mathematically you have to say, well, if you have this connection, then if the U belong to A, then you must have the second endpoint belong to B. Or other way around, if the first knot here belong to B, then you have to push the second knot here belong to A. You understand me? So the bipartite graph requires two conditions. The first one is about decomposition of the vertex. The second one is about the connection. And this is now very useful nowadays, because if you start from something like this one, not yet read the example. So read the picture I am drawing for you. So I have two knots for A and I have three knots for B, like this one. Okay. So this is the look to the picture I am drawing on the screen, people. This is the A and this one the B. No, this one not symmetric. This one not symmetric. This one we call the bipartite. Literal meaning mean okay. So the first A on the left, you have the knot U and A, for instance. You understand? You have to draw the picture in your knot, please. And in the second part, you have three knots, V, B, and C. Understand me? Then you have to say that the first condition of the bipartite mean the vertex knot will be the disjoint union of two subset A and B. Okay, A and B. So let's say U to be some student and A also some student. So the A mean the student. And if the student can do some job, then we connect like this one. That means U, student U can do the job V. So in reality, in the job matching, we can define the property of the vertices not the same. We define here capital B to be the job, understand me? Where you define define the capital A to be the set of students. Look to the chat box. So the bipartite graph is very interesting because it can capture the more complex case where you define the vertices consisting two different kind of vertices. You see? So read the chat box. We talk about the splitting. Then we talk about the connection. Look to the picture and read the chat box as well. If we say the edge like this one in the picture, so in reality we say that the student U can do job V. You see? So what is about the second connection A to C? Look to the picture. Understand me? So see the example on the screen and then read the explanation in the chat box. I give you the second example here. When we talk about the second connection, when I confirm that in that meaning, then the student A can do job C. Understand? So you understand why we do not allow the connection between student A and student U, because by the concept the two nodes U and A belong to A. Not allowed, okay? So that's the concept by time. I go back one slide to remind you about that before we move on. The important condition is from here, the second condition, okay? We do not allow the connection between vertices in the same part. If the connection like this one, UV, then both must belong to different nodes, okay? So like this one, other way around like this one, okay? U and V cannot belong to A. U and V cannot belong to B at the same time. So we're going to buy back time. Now we move to the example here. We talk about C6. I ask you to prove formally, will this one, can we conclude to be buyback time? And how can we prove buyback time? First of all, if you denote the vertex here by the notation like A, B, sorry, I have to write again the note so that you understand the theory. A, U, V, then B here, and C here, and X here. Okay? So I denote the vertex here in the C6 like this one. And by the concept, you have to define A and B so that the second condition is satisfied. You have to define A and B so that this one, the second condition is fulfilled. The second condition must be met to the first one. Okay. So tell me what can be A and what can be B. To through example on the screen. So Phạm Hữu Đức say well, Đức, you have to be careful about the notation of the vertex. You don't get the bonus point because the right answer you have to use the bracket to round like this one. Okay, a subset. He mentioned that A. So let me write A right here. Then X here. And also he say B as well. So this one become A. Đức almost correctly answer, but not perfect. So that's why he not yet get the bonus point. He mentioned that the second part must be like this one. VUC. So I brought for him here on the picture, this is U, because you see A and U connect, and then V here as well. How about AC? We don't have AC. So this one not C6, okay? This one is the one we call later K33. The C6 you have to delete R1 connection. Delete the AC. You don't have the AC. So the right hand side picture is not C6. That is the one we call K33. So this is the vertex C5. You see? The X here connect to U and C. That 5, but the X does not connect to V. So you don't have this one. No, you don't have. So that means the second one here must be disconnect. Okay. So actually, the right hand side is not C6. But if you delete the connection AC and the connection SV, and also you delete the connection UB, then you get C6. Okay, so that is the answer for that. You have to write the solution yourself, define A and B like my suggestion, and then you write the argument later. Okay, to finish that exercise, you have to specify clearly the setup connection. Yourself, do it yourself. Okay. Now this one is the KT3 where you allow all connection allowable. Okay. A, X, B, is that right? One guy. And then the other side you have U, X, no, VUC, V, the second one we did not buy ASB, and the second one VUC. You have to write like this one, and you have this one we call KT3, because the first condition should be the same. Okay, we cut this one, and you have here small m to be number 3. You see, there are 3 vertices here, and the other side you have here also 3 vertices. And the second condition say that you allow one vertex in the first subset A can connect to any other one in the subset B. So therefore, we conclude that by the reduction rule, the total number of connection will be m multiplied with n. Okay, and you get in total 9 connections. Look to the slide. Okay, that we call KT3. So the complete mean we allow any possible connection from one side to the other side. You see? And by the same idea, you can draw something like this, or you can draw the picture something like that. Okay, you have to do that yourself to understand the idea. Then this is the exercise. Yes. You ask something?
I want to ask that. So the complete by part-time is when two subsets have the same size, right?
So the idea is that this one we apply the zero idea, okay? And you don't forget the zero concept about bipartite first. You understand me? So you decompose the vertex like this, understand? So the A mean the left hand side here, and the B here on the right hand side, right? So this is bipartite. Then we want to specify the number of vertices on the left, so that's why we can write like this one, understand? Then we do the same thing for the vertices on the right hand side. So this picture tell you a specific case, but I want to tell you is about the zero case. So if you choose m small here to be number 3, n here to be number 4, okay? Then you have to redraw another picture yourself. You cannot employ the picture. Understand?
Understand.
Okay.
But I mean, is the difference with part-time graph with complete by part-time graph? What's the difference?
The difference is that in the complete bipartite we allow anyone in one side like this one connect to any other vertex in the other side. Okay, so that mean in the complete bipartite, if you follow the general notation like this one, the KMN, in the complete bipartite, you have for the second condition here, you can write down the condition here. I write down in the chat box for you in the complete bipartite. The degree of U must be to be n for any node U in the set A, understand? And the degree of V must be M for any notch in the second part. Can you read that from the chat box? So the maximum degree can be obtained in complete buyback time. But in a zero buyback time, not complete, then you don't have that one. In a zero buyback time, then the degree of the vertices in each part, the condition become inequality, not equality. Okay, when you have the not complete buyback time, then I write the condition for you now, and you can observe. This is the condition. You see the difference, right? So apply here the degree of A, degree of X, degree of B. They are all become number N, number 3 here. But in the previous example, like the C6, you don't have that for the C6. For the C6 here, you see that the connection between not A going to U and V, degree of only number 2, you see? For the C6, only number 2. You see here, one connection to this and one connection to that. And that is the generic part of time. For the complete, that means the degree must be maximized. Okay? So we have to finish now because time run out. Are you okay with that answer?
Yes, I'm okay.
Okay. So complete means maximum the degree for the vertex in each side of the story. Okay. And you have to do this one yourself, and this one will be for next week. Okay. From the slide operation to build up new graph. From the on one, you will learn on this Thursday, April 22. Okay, so any question, please ask. You have a few minutes more to go. Any question? So today we finish the basics terminology, and we end up with the buyback time. And there are about 10 exercise for you. 10 exercise. Okay, try to do figure out at home yourself. Maybe 5-hour working homework. And we finish the argument about makeup day. I suggest that we make up one day before. So April 28 we'll make up for April 29. April 29 means Thursday. So I will remind you, don't worry, the same time but different day, one day early. So next Tuesday we study as usual, okay? So see you on this Thursday. We continue the story of draft on this Thursday. Okay, and you should be here. Any question?
Teacher, so we will study at 28 April instead of 29 April, right?
Yes. I mean, only one day because on the April 29, I have a business trip. So that's mean next week we study on Tuesday and Wednesday. Okay, next week. Agree? Understood? Okay, good. So the other student, any student, ask other thing. Otherwise, we stop here and see you this Thursday, 9